topics and some recent work on them. So the first will be copy protection. So copy protection for programs, really the goal is to prevent someone from getting a piece of software and sharing it with all their friends. Classically, this is a typical way we would have done this is by having verification codes or something like that. But at the end of the day, a program is just a sequence of ones and zeros. And you can, classically anyway, and you can copy this as much as you want. So all of these, unless you're actually going to require like the program interacting with an online server or something like that, if you want a completely offline program, really at a fundamental level, classically, there's nothing you can do to prevent someone from copying the software. Everything really is just a roadblock. So before jumping into the quantum world, there is a classical half solution to this problem, which is something called watermarking software. And the idea is just like watermarking a picture, where you put some watermark, like your property of Mark Zhandry. With a picture watermark, what is the goal? The goal is that if you were to try to remove the watermark, the picture's destroyed and not really worth anything. So in much the same way, we can hope for watermark software where there is some mark embedded in the software that people can detect, and yet there's no way to remove that mark without just completely destroying the functionality of the software. Why does watermarking maybe help with protecting your software from being copied? Well, if I give you some software that's watermarked with, I don't know, some private information about you that you don't want to get out, well, you are probably going to be hesitant to try to release your software to your friends because your friends would be able to read the watermark and see that they're, to learn whatever private information you might have. Or if it has your home address and one of some watermark softwares floating around there on the web, and the law enforcement gets their hands on it, they'll know who leaked it and who to go prosecute. So watermarking software works as a deterrent to piracy, but it doesn't fundamentally prevent it, right? You still could copy your program as many times as you want, send it to all your friends. There's just an incentive not to. And what we before I get into that, I should say that we have a lot of positive results for watermarking, sort of similar to the case of obfuscation that we talked about in the morning. The positive results tend to be more or less only for cryptographic functionalities. There's also evasive functions sometimes, but more or less, most of the results are for cryptographic functionalities. And really, the reason for this is maybe not so surprising. It's that we're like a lot of especially this work here. A lot of these works actually used I/O, so you're using techniques that are sort of limited to obfuscating cryptographic functionalities. So maybe it's not a surprise. There are things beyond what we can beyond obfuscation. Like there's this notion of traitor tracing that you can kind of sort of see as a version of watermarking for decryption functions. And this we can actually do with much better tools. And I'll note that for watermarking, unlike for obfuscation, so remember for obfuscation, we said it's trivial for learnable programs. It's interesting for a whole host of programs, including evasive ones. For watermarking, it's actually impossible for learnable functions, right? Because if I give you program code that computes some function, but maybe has a watermark embedded in it, well, I can query that code on a bunch of inputs of my choice. Certainly, that's what it allows me. It allows me to do at least that. And if it's learnable, I can learn the original program from just Oracle access to the program, and that allows me to construct the original unwatermarked program. So, we went from something that for obfuscation was trivial to it actually being impossible for learnable programs. And then it turns out that it depends on how you define watermarking exactly. And there's certainly some versions where evasive functions make sense.
Sorry.
Yes.
Maybe I didn't listen for a minute. So you're saying that it's impossible for learnable functions according to some definition?
Yes.
But if you count queries or something like that, maybe it's not impossible.
Yeah, except like there's no
So I
right.
mean, it's possible in some strict sense, but it could be
Yes,
to look at the amount of resources that
it
are
could be.
required
Yes,
to learn the function versus to remove the watermark, then you could.
you could get into a fine-grained sort of setting where, yeah, like it's technically possible to remove the watermark, but it requires, you know, it requires a year of computation to do so.
Not about a year, but it requires more queries by an order of magnitude than to learn the function.
Well, no, because once you learn the function, you've removed the watermark.
That's right, but it takes some amount of work to learn the function.
Yes.
And versus takes amount of work to remove watermark.
Oh, and you're just saying that those should be
And then
close.
talking about if the gap is such that removing the watermark is as hard, then in some sense you're in good shape.
Yeah, fair enough. Fair enough. Yes, yeah. So I, you know, and I'm not really giving formal definitions anyway. I'm thinking of the usual way we define things, where it's, you know, for all PPT adversaries, there's an inevitable function. In that regime, it's impossible for learnable functions. But yeah, certainly you could say interesting things in sort of a more fine-grained.
Right, so the watermark is something that you would insert into the code that has no effect on the input-output behavior.
That's what you would hope for. That's not possible, it
That's
turns
not
out.
possible.
Yes.
Computation, I mean, it would be hard to find it.
It'll be hard to find.
Yeah. So
Okay, so you do change the input-output behavior.
you do, and that's inherent, at least assuming IO exists. So if IO exists, then you can take any, if IO exists and you had a watermark, a supposed watermarking scheme that perfectly preserved the functionality,
Yep.
you could just IO that, and then that doesn't have a watermark anymore. Right. So the way that all of these approaches work, this approach based on obfuscation, and even in the traitor tracing setting, it's what you end up doing to embed the watermark is you change it on a very sparse set of inputs.
Yep.
And the idea is that you also need that those sparse sets of inputs can't be distinguished from like inputs you would care about.
Right.
And then you sort of use the outputs on that in order to. Yeah, and I should also say, so with evasive functions, it's a little more nuanced. It depends on exactly what kind of watermarking you want. But in general, for exactly this reason, evasive functions are, you can take them as being unwatermarkable as well. Because for an evasive function, you expect on most inputs for the output to just be 0. So how are you going to meaningfully embed a mark in there undetectably if the output's just always 0 no matter what? Okay, so then Aronson proposed using quantum information to prevent copying in the first place by setting your program code to be a quantum state. And then the hope is that you can use the unclonability of general quantum states to conclude that you can't copy the program code.
Sorry, but I still want to insist
Yes.
about the watermarking. Why do you want to watermark?
I mean, we really want this. I am mentioning watermarking. It'll also be relevant in a bit, but I'm mentioning watermarking just because there is a classical solution that does something to prevent piracy, but it really only serves as a deterrence. It doesn't actually prevent you from pirating. It just says if you pirate, it can be detected.
So I guess what I'm saying is, what kind of software do you want to watermark? Is it the kind of software that has something to do with security? Or is it kind of software that has something to do with data and ownership? You see what I'm saying?
I mean, ideally, we would want to be able to watermark anything, but we don't know. We only know how to prove watermarking schemes for certain cryptographic functionalities. But ideally, you would want to protect any software that you might come up with, whether it's cryptographic or not. That holds true in the watermarking setting. It holds true for quantum copy protection, which I'm about to talk about. But the fact is that, sort of because it's related to the fact that with obfuscation, we don't know how to obfuscate programs.
I guess I don't understand what that means.
What do you mean?
If the program is a function, and you've just told me that it's impossible for a learnable function, then you're saying that you can only hope to watermark things which are cryptographic in nature.
I mean, maybe if you take cryptographic generally to mean something that's non-learnable, sure. But like maybe what would be an example? maybe I have a fast algorithm for multiplying matrices, or just I want to protect my operating system or something like that. I don't know if these are, so certainly like an algorithm for multiplying matrices fast is, I mean, maybe that doesn't fit into this framework anymore. You can learn that as multiplying matrices, but you can't learn small code. But that's not the regime we're talking about anyway. So that was a bad example. But thinking about an operating system, or some complex piece of code that is maybe doing very complicated computations, but they're not by definition, they're not like, it's not like I'm trying to build a pseudorandom function. I'm just trying to build code that does something functional. I
think actually the example of the sorry, that's it. I'm not asking after this, but I think that the example of the matrix multiplication is a good example. So it's working really fast, right? Mm-hmm. And you don't know how. And somebody wants to say that that's their proprietary idea, but the input output is just you put in A, B, it comes out 8 times, and you can't measure time. There's no side channel or anything.
Right. So that's a good example from that perspective, but it's a bad example from the perspective of we're not paying attention to sort of polynomial differences, where there's a trivial algorithm that's not watermarked for multiplying matrices, which is just the grade school algorithm.
So there's no advantage in that algorithm for this definition.
From the vague setting that I'm thinking about. Okay, so what we want though is to use quantum information to just prevent you in the first place from copying the program code. So there are some challenges. So one is oftentimes if the class of functions you want to copy protect is rich enough, it'll actually imply quantum money, a public key quantum money. So for example, if you're trying to copy protect a signing algorithm, you could just test whether it signs a random message or not as your verification of the quantum money state, and that will be publicly verifiable. So to get copy protection in many settings, not all, but in many settings, we're sort of stuck at this barrier that we're going to have to imply public key quantum money, which we said in the morning was non-trivial.
Also work for a pseudo-random function?
Not necessarily, because you need to be able to verify the outputs. That's why signatures.
Yeah. Okay.
So another problem is that it seems to imply obfuscation. So this is informal and vague, but if you could figure out what the program is doing from looking at your quantum state, you could maybe you could just write down a classical code for that and just send that and copy that as much as you want. So it implies some form of hiding something about the way the program works. And then lastly, there's still this issue of, even though we know how to do obfuscation, we know how to do quantum money, at least from strong enough tools, how do we combine them together to actually, get what you want? So quantum money, there's no functionality, right? Quantum money just does it verify or does it not? We have some functionality, and we want the functionality to be unclonable. So how do we like combine these different objects? And these are the problems that we face. And then I'll also note that copy protection is, for the same reasons as watermarking, it's trivially impossible for learnable functions. It does make sense for evasive functions. But yeah, for learnable functions, if you could learn, you could just take the quantum state, learn from it the classical code, and copy it as much as you want. Okay, so what's known? So Aronson proved back in 2009 that it exists unconditionally relative to a quantum oracle. So by a quantum oracle, I mean that the oracle is actually providing a unitary. And then we improved this to it exists relative to a classical oracle. So this is an oracle that implements a classical function, but you're going to be able to query it on superposition. And then, somewhat on the negative side, Ananthan Laplaka showed that actually not only are learnable functions impossible, but there's actually some non-learnable functions for which copy protection is impossible. And this result here, and both of these results, what they say is that certainly they're not saying that you can copy protect learnable functions, but they show relative to an oracle that you can't copy, or that you can copy protect any function that is non-learnable. But what this result shows is that when you try to instantiate that oracle, either of these oracles, with any real world structure, that security will fail, at least for some programs. That there are some classes of programs that, even though they're non-learnable, and therefore not trivially, therefore you can't trivially copy them, you can nevertheless copy them with some more effort.
Using the cryptographic assumption.
Yeah. There's an assumption here. You need you basically need well, you need like quantum FHE basically.
How are the feasibility results stated? They say exists for all non-learnable functions relative to oracle,
Can you repeat that?
yeah, how are the feasibility results stated? Like you say, for all non-learnable functions, they can be copy protected. Or
Yes. So the first two results say for all non-learnable, there exists an oracle relative to which for all non-learnable functions, we can copy protect those functions relative to that oracle. But then, yeah, so this result then says that, even though you have this result relative to an oracle, there's no hope of instantiating it in full generality with any standard model objects. That there will always be some functions that are non-learnable, which, according to these theorems, you could copy protect. But now, once you move to the standard model, you can't copy protect anymore. This is it's analogous results. It's more complicated, but it's analogous result to obfuscation. So relative to an oracle, you can BBB obfuscate. You can get ideal obfuscation for any circuit rather easily. But once you instantiate your obfuscation with any actual real world structure, the Barak et al. Impossibility says that there are programs that you can't obfuscate. And it's the impossibility here is kind of the same idea, but you have to work harder now that there's quantum information involved.
non-learnable are defined for quantum learners.
Yeah. So I mean, yeah, I'm not really rigorously defining learnable, but what I mean is when I say learnable, I mean that. That there is an algorithm that makes queries to the functionality and is able to find their program code. And yeah, I will allow the learner to make quantum queries. Okay, so what the Anantha-Plaka result says is that we really don't want to use these super complicated oracles to justify security, because we don't necessarily know what it means once we move to the real world. Then there has been some more recent work. So here, Coladangelo and all, what they showed is that using random oracles, you can get copy protection for a certain class of evasive functions with some security. It turns out it's not I won't really talk about this result, but it's not the kind of security you want. It's like it basically says that in some sense, that there's no way to perfectly copy, but there's still some room here to maybe approximately copy your functions. And then a little more recently, we showed that using I/O and various quantum money techniques, and quantum money techniques, and also techniques from the obfuscation literature, that we can get copy protection for certain types of PRFs, certain decryption functions, something called signature tokens. And I should say that when we published our results, we had to make an information theoretic conjecture in addition to assuming I/O, and then Kolf and Vidic later proved our information theoretic conjecture. So this is kind of more or less the state of the art. So just like with obfuscation, just like with watermarking, we now know how to copy protect certain cryptographic functions. We also know that it's impossible for certain functions. But we still don't really know how to copy protect general programs that may or may not be PRS decryption or signing algorithms. So I did want to talk about a special case which I find super interesting. So it's something that's called unclonable encryption, and it doesn't immediately look like copy protection, but you can sort of view it as a special case of copy protection. And even here, even for unclonable encryption, which is a really natural, simple object, already the problem seems very challenging. There's a lot of interesting questions here. So what is unclonable encryption? So it's a secret key scheme. So we imagine that Alice has a secret key K. She has some message and she encrypts it to get a ciphertext C. And we'll think of M as being classical, but C is going to be quantum. Right, and then an adversary gets its hands on C. And what is the adversary going to do? The adversary is going to try to split the ciphertext into two pieces, C1 and C2, and give them to two more adversaries. I'll call them B and C. And then B and C actually later learn the secret key K. And okay, so one thing that can happen here is our adversary A gets the ciphertext, they forward the ciphertext to say C down here, and they give nothing to B. In which case C, once they learn the secret key, can decrypt and learn the message, but B learns nothing. And essentially what we want is that's the only thing you can do. That no matter what the splitting adversary who doesn't know the key is, no matter what they do to come up with two ciphertext, and these C1, C2, they might look like valid ciphertext, they might look like total nonsense, but they split them in some way into C1 and C2. No matter what they do, essentially all that ends up happening is one of the users might learn the message and the other adversary learns nothing. So why is this interesting? Well, the original motivation of Gottesman was that you basically wanted to know if someone stole your information. So if you encrypt some message, and then an adversary was able to like steal that encrypted message from you, and then maybe the adversary through some other means learns the secret key, maybe it gets compromised in some way. Well, you would always be able to tell if an adversary stole the ciphertext from you. Because if they were able to steal the ciphertext in some way that allowed them to learn anything about the message, you would know that encryption on your own device must fail. Because you can think of your own device is B here, modeling it as an adversary makes it only strictly stronger. And here's the remote adversary that stole your data. So the fact that, if you're here and if you're able to decrypt your ciphertext, you automatically know that an adversary here that may have exfiltrated some of the data about your ciphertext, you immediately know that they actually couldn't learn anything about your message, even if the key was later revealed. Yeah, so this was the original motivation of Gottesman, and then Broadbent and Lord said, well, why don't we just make all these parties an adversary, make the problem more challenging. Right, and there's sort of an informal connection. It is a little more formal, but I'm hesitant to make any concrete claims about one implying the other. But basically, one-time secret key unclonable encryption can be thought of as copy protection for point functions, right? So why is that? Well, if you had copy protection for point functions, you could set your point to be your secret key. And then you could copy protect basically the function that that identifies that one point and outputs the message if it identifies it. I guess here we technically need a point function that outputs many bits. And it kind of goes both ways. If you had a one-time symmetric key unclonable encryption, you can view the ciphertext as an obfuscation for the point function that takes its input the key and outputs the message M. Right. So really, one-time symmetric key unclonable encryption can be thought of as just a special case of copy protection. So what do we know? So Broadbent and Lord showed that you know, a really basic scheme kind of based on, you know, Wisner's quantum money scheme or BB84, you know, kind of the natural thing you would try to do. Satisfy some form of security. Something that I believe it's their term, but certainly I would call it unpredictability security, which sort of says that the two adversaries can't simultaneously learn the message except with negligible probability. It's not as strong as what we would want. So it could, you know, with their scheme, it could still be that, you know, each adversary learns some piece of the message, but they just can't both simultaneously learn it. And then they strengthen their scheme using random oracles, but it's still a rather weak form of security. Okay, so here's their scheme. It's basically just the quantum one-time pad. So you know, it's just encryption bit by bit, and every bit you either flip the bit or not based on part of your key K1, and then you encode it in either the computational basis or Hadamard basis based on a bit of K2. Right. And what did Broadbent and Lord show exactly? They show that no split state adversaries can simultaneously predict a random message. So if the message is random, both the no split state adversary can have the two adversaries B and C simultaneously predict M with probability more than this 0.85 number, 0.85 to the n, which you know, this is, I forget what the constant is, a half plus 1 over 2, like a constant that comes up in the monogamy of entanglement games.
But certainly if we had a stronger security requirement, so like they can't learn any of the bits, well then that wouldn't be satisfied, because we could make it so that the first one can learn the first half of the bits and the second one can learn the second half, right?
Right, and that their scheme would be like that, right? Because you can just because it's encrypted bit by bit,
Right.
you can just separate the bits into two pieces.
Right. Yeah, exactly.
Right.
So
If we
when you
wanted
say,
to fix that, then we would.
You have to do something. You can't do bitwise encryption, right? You have to do something more
Yeah,
sophisticated.
yeah.
you say random M, so if M, you knew the probability of M to be 0 was 3/4, then what would it be? So only if it's 50-50 M.
That's what they analyzed. I'm not sure if yeah, I'm not sure what you could say if M is not in it. Certainly M has to have has to have a pretty substantial amount of entropy. So you can't get like worst case like we would like in crypto, where it's, you know, M is either M0 or M1.
No, I understand M comes from a distribution, but I was wondering if you need really for it to be uniform where you can create a distribution. I mean, some sentence, some theorem relative to the entropy of it.
Yeah, there is. I believe there's a generic. If M has high enough entropy, I don't know how high it needs to be, but if M has high enough entropy, you can I believe you can generically get sort of a, you know, a looser bound here.
Just like encrypt the random and then extract from it. And
Yeah. So great. So I'll get to that in one slide. So you know, the other thing that we just talked about is that there's also right. So there's a split attack where you can just, because you're encrypting bit by bit, you can just take, you know, some set of the bits, send them to one adversary, some set of the bits, send them to the other adversary. And it's easy for each adversary to learn, you know, their part of the message. And we would ideally like to prevent this. And there's even a harder problem. I mean, it's not harder, but a different problem, which is even if, you know, but let's say both adversaries just cared about the first bit, forget everything but the first bit. You can even do something that you wouldn't expect. Here's a really simple attack. Basically, so our adversary A, who gets the original ciphertext, what they're going to do is they're just going to guess which basis you use for, say, the first bit. You know, we're throwing everything else away, just focusing on one bit. They're going to guess what the basis is, and they're going to be right with probability 1/2. And if they're right, well, I mean, they don't know if they're right, but they're going to measure the ciphertext in that basis. If they guessed wrong, they're going to get random garbage. But if they guess right, what they're going to get is actually M, but XORed with the appropriate key bit. So then what the adversary is going to do is they're going to send the measured bit, I called it D, and which basis they guessed to, which is a classical value now, right? So they can send it twice. And then the adversaries are going to say, well, okay, if I now, the adversaries B and C, they know what the basis was. They know if A guessed correctly or not. If A guessed correctly, they can both decode and learn the message. If A guessed incorrectly, then they give up and say, okay, I'm not going to learn the message. And what this means is for any I, the parties B and C are able to simultaneously, unambiguously learn the message bit with probability a half. And this is just something that you wouldn't expect to happen in sort of an ideal scheme where you can either send the ciphertext to one or send to the other. And there's a little more sophisticated attack that actually gets this 0.853 to show up. So when I say unambiguous, it's because you know when you were wrong, as you get this bot. But you can actually do a different attack where you don't know if you were right or wrong, but you can actually exceed a half probability, and you can actually get the probability that both parties simultaneously guess the right message bit to be as high as 0.85. Yeah, this is just, if I was only sending the bit to one party and the other person learned nothing, one party learns the bit with probability half, or with probability 1, the other party learns the bit with probability half. So there's no way to get to 0.85. So the scheme gives us a rather weak guarantee about unclonable security. Okay, so the next natural idea is, why don't we use the fact that we get some sort of unpredictability and then extract from that unpredictability uniform randomness using an extractor? Or even better yet, let's just throw a random oracle in. And random oracles are fantastic extractors. So how are we going to encrypt now? This was also in Broadbent and Lord. What we're going to do is we're going to choose a random string X. We're going to encrypt X using the scheme from the previous slide. And then we're going to use X as a seed, or not a seed, as a source of randomness for an extractor, and use the extracted value to actually XOR the message out. Right, so I won't really get into the details of this, but so Broadbent and Lord were able to show that this does get you better security, but it's still not all the way to what you would want. Right, instead of this 0.855, it's something much better, but it's still not this ideal notion of either B gets the message or C gets the message and the other party gets nothing. And actually, it turns out that you can't do that with this scheme. So with this scheme, you cannot actually get the optimal security notion. It's not at all trivial to see this. I don't have a great intuition for like if you were just to look at it, I don't know that there's like a nice explanation for what goes wrong. But it turns out that there, even with this, this extractor notion, which like sounds like it should make sense, it turns out that you can't prove security. And one of the sort of conceptual difficulties with using an extractor here is that, so one, we need this extractor to be secure against quantum side information. Okay, let's not worry about that. That one, there's been literature on that. But the other one is that we're extracting from a string that one of the parties knows and the other party doesn't know, or we're hoping that one of the parties doesn't know. But it could actually be that like each party B and C, each of their view of the string X actually doesn't have men entropy, right? Like think of the adversary that gives the ciphertext to B with probability half and gives the ciphertext to C with probability a half. And then if you're given the ciphertext, you decrypt it correctly. If you're not given the ciphertext, you just make a random guess. So from each adversary, they have a probability of 1/2 of guessing X correctly. But extractors require a lot of min entropy. right? You need to be able, you need X to have min entropy conditioned on your view that's greater than the length of the string you're trying to extract, but our min entropy is only a half. So there's, you could try some sort of thing where you try to condition on which party is able to extract or not, but it turns out that when you try to do stuff like this, it just doesn't really work out. And I guess it's for it turns out there's a reason it doesn't work out, and it's for that the scheme actually cannot be optimized.
Can you say a little more about like what kind of attack is always allowed?
Yeah, so what they show roughly is, so there's this concept of a density matrix that generalizes pure states to look at probability ensembles over states. And basically, so I'm sort of fuzzy on the details, but they show that if that density matrix has high eigenvalues, then you can attack this. This does have high eigenvalues. That's as much as I can say about it because I'm not too familiar with the details. All right, and I don't know if it gets worse exactly, but there's another barrier here, which was to me very surprising. And it says that if you have a deterministic scheme, and we're talking quantum, so we have to be a little more precise about deterministic. So if you have a scheme where the transformation on the message is unitary, it can even be a little more general than unitary. Maybe you pad your message with the zeros and then apply a unitary transformation. But the point is it's reversible and deterministic. So if you run it on the same message twice, you'll get literally the same state as the output. If you want such a unitary scheme and you want it to have statistical security, you have no hope. And I found this quite surprising because on the other hand, like with ordinary encryption, even if you're encrypting quantum states or whatever, if you want one-time security, you actually can do it statistically and deterministically, right? Like in the classical encryption setting, we only introduce probabilistic encryption as a necessity when dealing with many-time security. And if you're only having one-time security, you can get away with determinism, and you can even get away with statistical security, but it no longer holds here. And this again, it's a little hard to give an intuition for what's going on, but basically, even if you apply a random unitary to your message, which a random unitary would require an exponential number of bits to even write down, but even if you apply a random unitary to your state in order to encrypt it, it turns out that there's like an information theoretic attack that would allow you to break the scheme. Right, and so then we go on to give a positive result that actually uses these subspace states again. And the positive result sort of circumvents this issue in two ways. One, it uses random coins, so it's not a unitary scheme. And also it uses a random oracle, so it's definitely not statistically secure. We can't even prove it under computational assumptions. And what's the scheme? It's sort of a natural, I'd say the hard part here was proving anything. But the scheme is sort of a natural generalization of the Broadbent-Lord scheme. So what we're going to do is we're going to use subspace states, except they're a little different, and we call them coset states. So instead of having your x, instead of having your values range over the subspace, they're going to range over the coset of the subspace. So the coset is defined by S. And also, we're going to put a complex phase in here, this x dot s prime. S prime basically is going to represent a coset for the dual A perp. Right, and what's nice about these coset states is that if I perform the quantum Fourier transform, I actually get another coset state where it's instead of A, it's A perp, and instead of S prime, it's S prime comma S. So just Fourier transform replaces A with A perp and exchanges the roles of S and S prime. So how do I copy protect a message, or sorry, not copy protect, unclonably encrypt? So my key is going to be a subspace, And then I'm going to choose my cosets at random. At encryption time, I'm going to choose my cosets at random. So importantly, these are not part of the secret key. And then I'm going to give you the coset state as part of the ciphertext. And then I'm going to extract from SNS prime a random string, or a pseudo-random string that I'm going to use to encrypt it. Right, and there's some details here because SNS prime, you basically need there to be a unique representative of every coset that you actually hash here, because the hash function doesn't know anything about the subspace. Right, and so how do you decrypt? Well, if you know A and you have the subspace state, you can extract SNS prime without much effort. And then once you extract SNS prime, you hash them down and you XOR with the message, or XOR with the ciphertext. Right, so this is now, I guess, the state of the art, but it's still rather weak, right? Okay, maybe needing random coins isn't a big deal, but it's still in an idealized model. We only know how to prove it in the random oracle model. We don't know how to replace H with a computational assumption like PRF, or even like there's no real reason to think that you couldn't do it information theoretically with a independent function or extractor or something like that. But this is what we know how to prove. And I guess where the random oracle comes in is it like very easily helps us go from if you can't compute SNS prime, then H of SS prime is actually random in the random oracle model. We don't have such a strong extraction property for standard model functions. Yeah.
Are we passing the no-go result, or it's a different model, or what's happening? Like compare this to the no-go result of Mayans at all.
Mm-hmm.
Like what's up? Like why do we manage to get the secure scheme here?
Yeah, so really what it has to do with, again, I don't have a great intuition for their results, but the reason the way I think about it is this subspace state sort of starts off already not being bitwise, right? There's like all this entanglement in the subspace state, and it allows us to make much stronger statements about the hardness of finding these cosets than kind of the analogous statement that you would get from just doing things bit by bit. It's maybe like very loosely related to the fact that like the Wisner quantum money states, or BB84 or whatever you want to call it, the unentangled bit by bit states, they don't make a good quantum money scheme with public verification. Even if you were somehow able to like give an oracle that could verify, that oracle would immediately break the scheme, or here the oracle doesn't immediately break the scheme, and we utilize something like that in order to justify security. Okay, so I guess this is sort of open question number 4 now, is can we build unclonable encryption or roughly equivalently copy protection for point functions in the standard model with provable security? Would could you instantiate our scheme with an appropriate extractor and prove that it works, or the pseudo-random function or something like that, with or without computational assumptions, just something in the standard model?
I mean, we have a bunch of candidates for how to do quantum copy protection for point functions.
Yeah, but with provable security relative to like some assumption cryptographers. Yeah, like even IO. We don't know.
I mean, my proposal from 2009 was just take your key, pseudo-randomly, encrypt it or something, and then just treat the output as a description of a quantum circuit to be applied to the all zero state. Right. Okay, now just treat that as a fingerprint of the string, right? Mm-hmm. And then just go and test that if someone has any other string, right?
Right. So I mean, one subtlety, I'd have to look at it. I'm not sure that the definition that you prove necessarily is actually equivalent to unclonable encryption.
Oh, well, all right.
but
Well, it's
let's-
copy protection for point.
Yeah,
functions. I
but
mean,
but
that's-
well, but my claim is that the right notion of security for copy protection for point
Is
functions
unclonable.
is probably very close to unclonable encryption.
Okay.
But even that aside, yeah. So certainly you could nevertheless conjecture that your scheme satisfies this or the follow-up scheme with the classical oracle, but you know,
But no,
appropriately
you don't even need
instantiated.
an oracle there.
In-
I mean,
right.
I have no idea how to prove anything about it, but I would
Mhm.
be astonished if that didn't give whatever you needed, right?
Right. Yeah. So the question really boils down to, I mean, but if you had asked me, 3 years ago or even 2 years ago, I would. This astonished me. The fact that this is like the most natural thing that you would expect this to work. You know, you have something unpredictable, you extract from it, you get
Yeah.
pseudo randomness, and somehow it doesn't work. So you know, I'm not that confident one way or another, but yeah. So, but yeah, get it with provable security, even relative to IO. Combine IO, LWE, isogenies, LPN, anything you want. You know, construct unclonable encryption with optimal security relative to these assumptions.
I feel more confident in the inability of someone to find the structure in the random quantum circuit than I feel in IO.
Yeah, fair enough. Fair
Or
enough.
isogenies, but,
Why?
What?
Why?
Because it's a more structureless problem.
Yeah, I mean, I guess you know, what we're, you know, as cryptographers, we like to you know, rely on the history of an assumption having been analyzed by a lot of people, rather than, and, you know, maybe eventually random circuits will be the assumption that we use. But you know, even as of now, even though IO is questionable and a lot of people in the community don't like it, it still has had more eyeballs, I think. Okay. Yes.
It's even open information theoretically. It's possible.
Yeah, it could be information. You could have an information theoretic scheme as well. For all I know, you can take our scheme and make this a you know, an information theoretic extractor. For all I know.
I mean, for an information theoretic copy protection scheme, if the error probability were small enough, then you would just try it out on every single input and then you know, make copies in that way, right?
Right. So
So it can only work if you're willing to tolerate an error probability that is like, or you know, or another way to say it is that even if you had an information theoretically secure scheme, if you then just have like a polynomially many copies of the program, then it would become information theoretically insecure.
Right. I'm having a little trouble mapping between the unclonable encryption and copy protection. And the unclonable encryption setting, it's a little more clear, I guess.
All right.
But yeah, in copy protection.
Yeah, well, I mean, you know, all I'm saying is that if you have enough copies of the program, then you know you could just take the majority vote of all the programs on your input.
Yes,
And then
certainly.
you have an exponentially small error probability. If the error probability is small compared to 2 to the n, then I just try it out on every input, and then I find my secret, and you know, and I have no possible information theoretic security.
Right. I guess the sense in which I don't need to go back. The sense in which this is equivalent to copy protection, though, is really only in the one-time setting where you're getting one copy protected version of the point.
Okay.
Right. So yeah, I think if you're going to go to many time, you probably need computational security because of which also shouldn't be a surprise from like viewing it as an encryption scheme. Many times secure secret key encryption also requires computational assumptions. In the one-time setting, it could be unconditional. For all I know, it could be unconditional. All right. So I guess, yeah, I guess I just wanted to mention that there's a relaxation called copy detection, or what I call copy detection, which is basically, we're not actually preventing the adversary from cloning, but we want to be able to detect if they copied. It's sort of closely related to watermarking, but there's no deterrence here. It's just, you know, if the adversary is able to copy one of these things, both of these may be able to compute the program, but one of them won't look right. And you'll be able to tell that it's a bad program. And it turns out we actually made the connection to watermarking explicit. If you could watermark a program with public watermarking, meaning anyone can look at the program and extract the mark. You can also copy protect it. How? You set the mark to be the serial number for a quantum money scheme, and you give out your watermark software and your banknotes. So, this is classical. The watermark software is classical. So I'm not preventing you from copying the functionality, but if you copy it, only one of your copies will actually contain the valid banknote. And because it says, we watermarked the software where the mark is the serial number, the only way to sort of present a valid program is to actually present a valid banknote relative to the serial number. So there's this nice connection between this weak form of copy detection and watermarking. So we can just automatically use any quantum money scheme you want and any watermarking, any watermarkable set of programs, and you can then copy detect it. Who knows if we can upgrade sort of this blueprint to the copy protection? I don't know, sort of inherently only in the detection case. And then around the same time in Unclonable, they constructed something called secure software leasing, which I'll talk about in 1 second. Which in my mind, I think of as slightly different, and I'll explain why. I think about it as slightly different from copy detection, but they also use quantum money and some other standard tools to get copy detection for a different class of functions. Okay, so that's copy protection. I'm just going to very briefly talk about revocable cryptography. So this is the last area. So the idea here is, Alice gives Bob some quantum state that maybe does something. Maybe it's a program that computes some interesting function. Maybe it's cryptographic, I don't know. But then at some point, Alice wants it back. And Bob then does something to convince Alice that he either destroyed the program or actually handed it back to her. And once he's done that and Alice has verified that she has the right program back, or at least that verified some proof of destruction, now Bob shouldn't be able to run the program anymore. So revocable cryptography is really kind of a relaxation of quantum copy protection in the sense that Alice, if the way that Bob gave the program back was to actually give a program that evaluated the right function, then the fact that Alice has Alice can check the program, check that it does the right thing, and if it succeeds, she'll be convinced that Bob couldn't still have the program around. Otherwise, Bob would be breaking copy protection. So it's some sort of relaxation.
So some sort of leashing, like it's on a leash, and I can.
Yeah, I mean, so Alice doesn't have the ability to actually tug it back.
Right.
That's not going to be possible. But
only if he wants to.
Yeah, so he could misbehave and not give her anything, in which case he still has the program, can still run it. But if he gives it, maybe he gave Alice a deposit or something, and he wants his deposit back after running the program, Alice wouldn't give the deposit back unless Bob gave her a functioning program.
But the point about the analogy to leashing is that once he, let's say, decides to give it back, he really doesn't not have it anymore.
Correct. Correct. In some rigorous sense. Right. So, okay. So here's secure software leasing. And just so you can think of it as copy detection, except one of these programs requires a secret key to verify. So it's sort of like, right. So, right. So with copy detection, we had these two programs, and anyone could tell that, or one of the two must fail verification, and the verification is public for both programs. Secure software leasing is sort of this weaker version where this one up here only has to pass a private verification algorithm. This one has to pass a public verification algorithm. So this, basically this is the program that Alice expects back from Bob. She, knows all the secrets involved in the program, so she's able to do the private verification. But someone else, someone on the outside would be able to do the public verification. And Unclonable showed under standard tools that you can do this for a certain class of evasive functions. There's also this recent concept that's emerged called encryption with certified deletion, where you have the adversary gets a ciphertext and then at some point gives a proof that they destroyed the ciphertext. And you want that if they give you a proof and it actually passes, that even if the adversary later learns the key, they can't learn the message or any info about it.
Wait. If the message was classical information that they all had, that the adversary had full access to, then it's impossible in principle, isn't it? I mean, and yeah, they always could have saved a copy somewhere.
Well, but the adversary didn't know the key when they had to destroy the ciphertext. Right. So that.
Okay.
Right. So the adversary only gets the key down here at the end. At the beginning, they don't know the key, and maybe.
And is the thing that they hold a quantum state?
Yeah. Okay. So C is a quantum state. The proof may or may not be quantum.
So they held this quantum state, and now they're going to prove that they no longer hold it.
Right.
Which indeed they can do if they by a protocol that involves giving the state to someone else.
If the state could be verified,
Yeah,
yes.
Right.
Right. So a not hard observation is actually unclonable encryption gives you this. It's not quite trivial. You do have to work for it, but.
What's this K for? Like they could show the government that what's this K for?
K is the secret decryption key.
So I don't understand the story. So I sent you a copy. Ciphertext. What is C? C is
a quantum ciphertext.
And now pi is a proof that I destroyed it.
Yes.
And K is what?
K is the decryption key.
I destroyed it already.
No, you destroyed the ciphertext, not the key.
But why do I want the key if I don't have the ciphertext?
Well, maybe it gets revealed later. Like maybe it leaks later for some reason, or gets exfiltrated somehow from the honest person servers.
So K is something that I only get if I destroy C.
Not necessarily, right? The point, it's a way to model the fact that you actually destroyed your ciphertext. Even if you were given the C at the end, you can't learn. Even if you're given K at the end, even if you're given the key, you can't learn the message. Like that. That really says you destroyed the ciphertext, because if you had the ciphertext, you'd be able to learn the message.
Okay. So it's a definitional thing.
Yeah, and you could probably come up with some scenario where it makes sense. But
it's a definition. Okay.
Right.
So you could then have to send an error. You're saying even if I had the K, I cannot distinguish now between C0 and C1.
Right, exactly.
It's a challenge or something.
Yeah, and yeah, so unlike unclonable encryption, we can actually, we actually do know how to do this in the statistical one-time setting, statistical one-time secret key setting. And then in this recent work, the authors showed how to use cryptographic techniques to sort of look at the public.
So I have a question. So this is like reminds one immediately of deletion, right to be forgotten, these kind of things.
Mhm.
You're saying that that's possible, at least in this setting where you define it as an encryption.
Right.
And that might imply other things, like you could delete it from a data structure.
Yeah. I mean, it's sort of most natural for cryptographic objects to think about. You could certainly ask if you can prove deletion of some entries of a database too. I don't know if there's any hope of getting like a strong cryptographic kind of security definition though for like a general data set.
That could be indistinguishable from whether you had it to begin with or something like that.
Right, but I guess the problem is, like with some sort of data set or data structure, certainly if you have the feasibility of actually seeing what the data structure is, you can just write it down as classical bits, and then you can destroy it, but you still have the data around. So it's really sort of inherent that something gets hidden in order to have any form of security here. So it's kind of most natural to talk about it as an encryption scheme. Yeah, and I just want to mention one other work, and it's arguably the first work of this like revocable cryptography. Well, so it's due to Unruh in 2013. But so the idea is, okay, so in the classical world, we have this object called time-released crypto, where I encrypt a ciphertext. There's no key for the ciphertext, but it takes a long, long time to decrypt. Maybe a day or a week or a year or something. These are constructed based on certain assumptions about repeated squaring and groups of unknown order. And so Unruh had the idea of, well, why don't we make it revocable? So, I give you the ciphertext, now it's a quantum state. You can start working on it, spending your week or whatever the desired timeline was in order to get the message. But then, someone says, hey, give me that ciphertext back. You give the ciphertext back and you want that. Now, even if it was 5 seconds before you were going to figure out what the message was, you can't learn the message. Right, so he defines this notion of revocable time-released encryption. And the construction idea is exactly what you would expect it to be. It's you do a classical time-released encryption of a random key, and then you do, say, some encryption scheme of certified deletion. You encrypt M under the key K. At the time, no one was talking about encryption with certified deletion, so he actually had a specific protocol for encryption, but this is kind of the intuition for what to do. And the idea is that if you delete this 5 seconds before your time's up, then even though you eventually finish computing here and learning the key K, well, you don't have the ciphertext anymore, so you can't learn the message. It turns out getting the security proof to work is actually non-trivial. Again, it has to do with this combination of quantum information theory concepts and proving things the way we do in cryptography via reductions and stuff like that. Getting the security proof to work it's not a generic conversion like I wrote it here. You have to sort of open up this encryption scheme, and it's a non-trivial proof, but it's another example.
So I guess I've done all the work. I'm like almost at the last step.
Yes.
And I can still get it revoked to go to the beginning, or just to get destroyed completely.
Destroyed completely.
So it's not like you slow me down again.
You could imagine that too, but no, the way he was thinking of, you just lose it completely. No matter how much computation you did, no matter how close you were, once it's revoked, assuming you actually partake in the revocation, you lose the ability to ever learn the message. Okay, so I know I'm over time, but there was one, so that completes sort of the overview. I did just want to mention that there's another really exciting area, which is getting unclonable cryptography with classical communication. And this, I don't know, to me, this was like amazing that this could even be done. You think like, oh, I have unclonable states. I want to do interesting crypto with them. I have to do it via communicating those unclonable states. But somehow, amazingly, we now have some techniques for getting unclonable crypto with classical communication. Yeah, I don't know if I want to spend too much time on this, but this was just some sort of intuition for how this might be possible. But okay, maybe I'll just skip that since we're already much over. So this kind of all started with this work of Bukerski et al., who give this proof of quantumness, assuming LWE. And then, so the proof of quantumness isn't really an unclonable cryptographic object, but no cloning was sort of inherent in their construction. And it's since been, those ideas have been used to build, say, public key quantum money. And the dream goal is actually going to be publicly verifiable quantum money, where all the communication is classical. Communication with the bank, communication with the other parties. So to send a banknote, it's classical. This would be the dream goal. We don't really have a satisfying solution to this. In the private key quantum money setting, there is a solution by Radian and Sata. I think there's also another team there. And then in the public key setting, we can actually have the bank be classical. So the minting process is classical. So the bank can send banknotes just using classical information to people. But then when people want to go spend their quantum money, they have to actually. And I guess I should have maybe mentioned my own work. We construct relative to an oracle, publicly, the publicly verifiable quantum money, classical communication.
Sorry, the question here is, how can I pay using only classical communication and the
Yes.
money appears somewhere else?
Yes.
Okay.
Yeah, and the rough idea is that you can use interaction. So certainly I can't, if I have some quantum banknote and I want to give it to you, and I send you just a classical string, if that sent the banknote, you could just do whatever protocol you're using to reconstruct the banknote on your end, you could just run it many times and you copy the state. But using interaction, it turns out that you can actually put, in theory, do better. And the, I don't want to spend, since I'm already over, I don't want to spend much time on the slide, but basically like what Alice can do if she wants a banknote is she can generate a quantum state locally, send some classical value that's, a serial number, some sort of digest of that state. The mint signs it with a signature, and then her quantum money state is, whatever her state was together with the signature from the bank. And then, if this quantum state itself had some sort of signing ability, then she could send the banknote to Bob using some sort of similar process. That's kind of the gist of why this might be possible with interaction. Right. So this is my last big open question is, can we throw any cryptographic assumption you want, but standard model, no oracles. So IO, LWE, LPN, isogenies, multivariate, quadratic, whatever, anything that's been conjectured in crypto and studied by a reasonable number of people. Assume that, can you get publicly verifiable quantum money with classical? And that's it. That's the end of my talk.
I could mention, I just want to advertise one of my most annoying or open questions in this area. Can you get publicly verifiable quantum money relative to a random oracle?
Right. Yes, that's a great question. Yeah, so I thought briefly that my quantum advantage stuff from yesterday might be able to make anything of it.
Yeah, that's
but yeah, so the point I guess is that everything we have for building quantum money seems to require a lot of structure. Like it requires these subspaces, or the knot scheme is invariance and knot diagrams. There's all the structure going on. Can you do something without structure? Yes.
We have a break until 3:30.